Hey guys, sorry for the long hiatus. I know I promised to make my maze solver smarter, but I've been working on some other things recently, so I'm finally getting around to this, and I'd like to show you guys a way to make this maze solver a little bit smarter. So what we've done so far is we have the start in the top left corner and the finish in the bottom right at the red square, and when we press solve, we see the black path that it finds from the green to the red, and the yellow squares are everywhere it's explored. But obviously this isn't too smart, so it explored the entire rectangle here, looking for the finish. And it definitely doesn't need to explore the entire rectangle. So why is it doing that? Well, when we run solve_maze, this function, it adds the neighbors. Let's see, where is that? So first it looks for the finish, and then it comes down here, and it adds the neighbors from where it's looking. And then the next place it goes to look is just whatever's the next in the queue. And so it doesn't really even care where it's looking. It picks whatever random place is in the queue and just starts looking from there. And so it's really looking all over the place. And we want to make it look in a place that makes more sense. So what makes more sense instead of just looking at any random place? Well, if we reset here, it makes sense whenever it looks at its neighbors to choose somewhere that's closest to the bottom corner here. So, as it's going along and expanding, it doesn't need to start exploring in other random parts of the rectangle. So to do that, what we're going to do is, I think first of all, we're not going to keep two queues here, so we don't need an XQ and a YQ really. We're going to just make a queue, our line, and it's going to be an array of arrays. So we'll start off with the point 0, 0. And q.length, as long as that's got bigger than 0, we're going to keep looking. So we have more places to look. And this just keeps track of the places we want to look from. So we're going to look at 0, 0, the start, and look around there. And I'm going to just comment this out for the moment. And that's what we're going to make smarter, as we don't want to just shift whatever's next in the queue. But before we do that, we need to take care of all the XQYQ stuff that we have elsewhere, and there's not very much actually. In fact, it's only down here. We have 4 places we need to replace this. So we're going to say q.push the array of the x value is x location minus 1 and y location. And then we can get rid of both of these lines. And here we're going to push the array, that's the x location plus 1 and the y location. And here we'll push the x location and the y location minus 1. And the last place we need to change, we're going to push the array that's the x location and the y location plus 1. So we've already figured all this out before, which makes it easy to do right now. That should work just the same as it worked before, except now we have all this information in one queue. And the distance formula I'm going to use, so we want to find a distance formula to find the place we've explored that's closest to the finish, or at least closer than choosing any random place. I'm not going to make the smartest one because I'm going to make this easy, but I would leave it as a challenge to you to make it smarter than what I'm going to do. So I'm going to create a new function called findBiggestIndex. And it's going to take the queue. And it's going to find the index of the sort of closest point to the finish in the queue. Okay, so what I'm going to do is say var biggest index equals 0. And we're going to loop through the queue and see if there's anything closer than what's at the beginning. So before we were pushing essentially what is now biggest index, the first thing in the queue. And we want to find a better point. So for var I equals 0, I is less than q.length, I plus plus, we'll look at all the points in the queue, and if q at I0, the x value, plus q at I1, the y value, at that point I is bigger than q at biggest index 0 plus q at biggest index 1, then what happened? Well, biggest index isn't really the index of the biggest point, is it? So if I add these two values and it's smaller than the sum of these two values, that's not the biggest index. So I'm going to say that the biggest index is really I. So the biggest index equals I. And so that's going to loop through and keep track of whatever was the biggest sum. And then I want to return the biggest index. Okay, so if I run this function, I should find the index of the biggest thing in the queue. And that's what I want to explore. So instead of doing xluck is the shift of whatever is the next thing, we're going to say var index equals find biggest index of q. And the x location is going to equal q at that index. Of course 0, so we want the x coordinate. And then the y location is going to be q at the index 1, which will give us the y location. And so now these should be, in a sense, closer to the finish than what we've been popping off before, or shifting, I guess, from our queue. And now we need to get rid of that index in the queue, because we've already explored there now, or we're about to explore there, so we don't want to keep exploring from the same point over and over again. Otherwise we get stuck. So we're going to do q.splice index 1. So what this does is it cuts out a part of the queue, and it's going to start at index, and then take out one element, which will just erase whatever element is that index. So that's how we're going to remove it now instead of shifting it out of the array. Okay, so let's save that. And if we run it and refresh this, solve, notice now it solves the maze, but it's not exploring everything. So this whole part is still gray because it didn't look all over the place. It did explore a little bit extra. So why do I say this isn't the smartest way necessarily? Well, you could probably get there even faster by going kind of diagonal right through the maze. And that would probably be a more direct path, it would be a straight line. And we're still crawling along the edge here. And that's because we're just adding the x value and the y value. So this would be a value of, say 1 and 1 is 2, and this would be 2 and 0, or so on. So whenever it explores here, it's going to open both of these at the same time, and they're both going to have the same value. But let's see what happens if we make the maze a little different now. So it's a little bit tricky, and what we don't want it to do is we don't want it to start crawling along this wall and follow the wall all the way back up and start zigzagging around and exploring. Let's see if it does smarter than that. So good, it doesn't. It doesn't crawl up along this wall. It continues going this direction because it sees that this is closer to the finish than these points up here, and so it's probably smarter to stay around here and then head down and find the finish. So now our maze is smarter than what it was before, but we can still trick it. So it doesn't necessarily always do better, actually. So what if I do something like this? What do you think it's going to do? Well, of course it's going to head this direction and head down as it usually does to try to find the finish, but it can't get there. And then it's going to start exploring all these places that it thinks is closer to the finish. And of course it needs to actually go this direction, so you are able to trick it, and it still explores everything. So notice it actually explored this whole area. So that's another way you can make this a little bit smarter. I'll leave those sort of challenges to you, but at least I finally finished what I promised, and this is an A-star search, I guess. So it's there's a value associated to every point in the grid, and it tries to choose the smartest value, in a sense, or the one with the biggest number as like the best value. It's like the best reward or something.